Okay, now we're going to look at a specific example. We're going to look at how we would build a mixed model for an experiment where we have one experimental factor, but with 3 levels associated with it. So imagine we have 24 participants in this study. We measured their gaze duration while they were reading a sentence on a computer screen. And the sentence appeared in one of 3 conditions, one of 3 contexts. So the sentence appeared in a negative condition, a neutral condition, or a positive condition. And we had 24 items. The study is repeated measures, which basically means that every participant saw every experimental condition. So we can look at our data set and we can see it's in the right sort of format. It's in long format or tidy format where every row corresponds to one observation. And that's important that we have our data in the right format. So we've got 4 columns in this data set. We've got subject, item, condition, and gaze duration measured in milliseconds. And you can see that we've got multiple observations for each of our subjects. So this is just using the head function, so it gives us the first 6 rows of our data set. So we've got multiple observations for each subject at each of the 3 levels of our experimental factor. So what we're interested in is whether or not gaze duration is predicted by our experimental condition factor while treating subjects and items as random effects. So the first thing we're going to do is plot the data. So the code for this plot is in the markdown document, by the way. So you can kind of see that for our 3 conditions, we've plotted the raw data points. I've plotted a geom val-in to give us an idea of the shape of the distribution. The individual data points plotted using geom jitter, a little bit translucent as well, so we don't have the problem of overplotting. I've also added a black dot corresponding to the mean for that experimental condition and confidence intervals bootstrapped around the mean. So we can kind of see visually that the positive condition looks a little bit longer than the neutral condition, which looks a little bit longer than the negative condition. And it's always a good idea to generate some summary statistics or visualize your data before you actually build any sort of model, because it means you've almost got a bit of an expectation as to what you're actually going to find when you build your model. And if you build your model and it doesn't sort of map onto what you're expecting to see, it could be the case you've actually done the model incorrectly. So it's always a good idea to get the summary statistics, visualize your data, and then think about what that means so you've got a little bit of preconceived idea as to what the model is likely to tell you. So this is our visualization. So let's build our model, and it's relatively similar to what we had previously. So in this case, we're using the LMER function, so it's a mixed model, where gaze is predicted by our fixed effect of condition plus a random effect of our subjects, such that we're modeling a different intercept for each participant, so a different baseline reaction time. We're also modeling the fact that the difference between our 3 levels of our experimental factor, the differences between our conditions might vary from one subject to another. We're also modeling the random effect of our items, such that we're modeling an individual baseline for each of our items, and also modeling the fact that our experimental factor, our condition, differences might differ again for our different experimental items. So if we're to build that model, what we get is this little warning here, is singular. What this tells us is that the model that we're trying to build in terms of the number of parameters we're trying to estimate is probably more complex than our data set will allow us to actually build. In other words, the model we're trying to build is probably too complex relative to the richness of our data set. So one thing you could do is kind of ignore the warning. I mean, it's a warning. It's not a fatal error or anything like that. So you might decide to ignore the warning if there's a strong theoretical reason to model all of the terms in the random effects structure that you want to model. Another solution, though, would be actually to gradually simplify the random effects structure until the error goes away. So you can simplify the random effects terms by incrementally dropping, say, a random slope from your item term, rebuild the model. If the error is still there, you might then decide to drop the random slope from your subject random effects term. So you kind of do it iteratively like that until you find a model that doesn't generate the warning. So that's one way you might want to do it. So we could drop our random slopes, and if we do that, we actually end up with a model that doesn't generate the warning. So we've got a simpler model here where we've got a fixed effect. We're modeling random effects of subjects such that we're giving each subject their own baseline. And we're modeling the random effect of items, where each item has its own baseline. But because we've dropped modeling those random slopes, we're kind of assuming that the difference between the three levels of our experimental condition are the same for all subjects and for all items. And that can actually increase type 1 error rate, leading us to think that we have an effect when one isn't actually present. So you have to be quite careful if you simplify your random effects term too much, because you might then just have an effect that's spurious. It's not real. But in this case, we've dropped our random slopes. And we've got a model that doesn't generate the error. So one thing we should do is check our model assumptions. And we can do that using the performance package and the function check model from that package. What that will do will give us a number of diagnostic plots, very similar to the assumptions in the context of the linear model, and it'll allow us to quickly tell whether or not our mixed model seems to be consistent with the assumptions behind mixed models. So the first thing, absolutely the same for linear models, is that we're assuming our residuals are normally distributed. So we'd expect to see the residuals plotted along this line here. And in most cases, that's true. It's only at these extreme values that the model seems to break down a little. But I'd be pretty happy with this as indicating our residuals are normally distributed. And we can kind of see here, residuals do look roughly normal. Another assumption is homoscedasticity. I can never say that word. Where we'd expect to see the dots plotted equally around the red horizontal line. Okay, so that tells us about the linear relationship. That looks pretty good there. We'd also expect to see homogeneity of variance, where we'd just see the dots spread equally around the horizontal line. And it's not quite horizontal, but it's not looking too bad to me. And then we can also check the normality of our random effects for our subjects and for items. And you can kind of see in both of these plots down here, things are looking pretty normal. Most of those points are on that diagonal. I guess one thing that's worth pointing out is you will rarely build a model that clearly 100% fits all of your assumptions. Sometimes they'll fit to a greater or lesser extent. So you do have to kind of use your judgment. And I always think of the quote attributed to the statistician George Box, who said that all models are wrong, but some are useful. Okay, so it's worth thinking about in those terms. This isn't a sort of binary, classification. This model's good, this model's bad. It's never the case that it's going to be quite as clear cut as that. So you can look at these diagnostics and ask yourself, am I happy enough with them? Do they look generally okay? So in this case, I think these diagnostics do look generally okay. So we can ask for the output of our model. So we can use a summary function to get the output. We're given information about the random effects term here. So we see in this case more variability in subjects than in items. But this is the critical bit that we're interested in. So we see that in this case, the intercept corresponds to the negative condition. It's 1083. The neutral level is estimated 100.84, and the positive is 123.40. So what this means is that the average response times to our negative condition are 1083. Average response times to neutral condition are 100 milliseconds more than that, so 1183. Average response times to the positive condition are 123 milliseconds more than the intercept. So what that is what? 1,200 or so. And the t-tests here compare the intercept to our neutral condition, first of all, and then our positive condition. So this, it's worth pointing out, again, this is because of the default dummy coding nature of the way in which R chooses a reference category or reference level of our factor against which to compare the other levels of our factor. When we come on to factorial designs and mixed models, we'll actually see we can change the contrast coding structure to be a little bit more useful to us in terms of interpreting the model parameter estimates. But for one factor, we can kind of live with this dummy coding. We've got two comparisons, neutral versus negative condition and positive versus negative condition. Now, of course, you probably think to yourself, well, actually, there's one comparison that isn't present here, which is neutral versus positive. And that's one of the issues with using this kind of default dummy coding. So actually, only part of the story has emerged so far. So let's compare the model that we've just built with the fixed effective condition to a model without. So this is comparing experimental model again with a null model that we looked at in the previous video. So our null model is the same as our the model that we built earlier, except we've dropped the fixed effect. We've only got the two random effects in here. So again, remember, this null model has to be a subset of our full model. So you have to make sure that the random effects terms here are the same as they are in our full model. And the only difference is that in this case, we don't have the fixed effect. So we can build our null model, compare it using the likelihood ratio test to the model with the additional fixed effect. And we see down here that the models differ from each other. With the deviance score, so that's the residual sums of squares, the error is less for our model with a fixed effect than it is for the model without the fixed effect. So that's basically telling us that our experimental manipulation seems to be having a difference. And we kind of saw from the parameter estimates, we're getting a bit of an idea as to what level of our factor might differ from what other level. But what we really want to be doing is either doing contrast explicitly, or in this case, running pairwise comparisons, where we actually control for the multiple comparison problem. In other words, we're going to control the family-wise error rate by using either Tukey or the Bonferroni correction for multiple comparisons. So if we build our pairwise comparisons using the em_means function, so our em_means function with our model, pairwise comparisons by condition, we get the estimates for our three experimental conditions. This is roughly what we calculated earlier. Then we get the pairwise comparisons comparing each condition with each other condition in all possible combinations. And the default correction for multiple comparisons using the em_means is Tukey. Okay, so we're going to use the Tukey method as a way of correcting for multiple comparisons. And if we correct for multiple comparisons, we see that only one pairwise comparison is significant, and that's the negative versus the positive condition. The negative versus neutral one that was significant in the model estimates we looked at earlier, once you take account of the fact you're doing both comparisons, now isn't. So we can kind of see that we've got a model where our experimental factor does have an influence on gaze duration, and it's driven by the fact that people are quicker reading sentences in a negative context than they are in a positive context. And that's what that pairwise comparison tells us here. That's the difference, that's the pairwise difference that's kind of driving our effect. So again, just to sort of wrap up this little section, just to remember, when you're using the likelihood ratio test, you can only do that if the models are nested. In other words, if one model is a subset of the other. Models that have different fixed and random effect structures, in other words, ones that aren't nested, can't be compared using the likelihood ratio test, but you can compare them using the AIC and BIC values. If you recall, AIC is the Aikiki information criterion, and it measures how much information is not captured by our model, meaning that lower AIC values suggest a better model. But it's also worth noting that absolute AIC values cannot be interpreted of themselves. AIC values can only be interpreted relative to the IC value or values from other models. AIC and BIC are quite similar to each other. AIC will penalise models that bring in new parameters, but BIC, Bayesian information criteria measure, will actually penalise even more. Okay, so that's a general introduction to linear mixed models. Hopefully you can see how we've gone from sort of linear models with categorical predictors, continuous predictors, hopefully fairly straightforward, based on stuff that we covered previously. We can take it up a level. We can model the individual variation due to participants. We can model individual variation differences due to items and build up a model that is kind of able to take on board all of the information in our data set. You know, ANOVA works over aggregate data. Mixed models work over raw data points themselves. So it's an approach that's using a lot more information that's actually in the data set. We can compare different models to each other using the likelihood ratio test, IC, BIC values. And we can look then in this section at how we would build a fairly straightforward mixed model to account for the fact that one experimental factor with 3 levels was able to predict people's gaze duration reading sentences in one of 3 different contexts. And we were able to build a random effect structure that was able to capture the individual differences between our participants and between our items. So hopefully you're convinced the mixed models themselves are not overly complicated. The maths underlying them is, but conceptually they're relatively straightforward, and they're based on these regression ideas we've looked at several times during the course of this unit. So that's kind of a general introduction then to mixed models. In the next session, we're going to be looking at mixed models for factorial designs. We're going to be looking at how we change the contrast coding schemes. We're going to move away from this default dummy coding. We're also going to look at how you build mixed models where your dependent variable isn't continuous. So we're going to look at sort of binary outcome dependent variables. And we're also going to look at mixed models for modeling ordinal data, such as you might find or collect using a Likert scale, for example. So I want you to work through the rest of this worksheet, be comfortable using these new packages, and hopefully you'll kind of see how it's all connected. And then we'll move on next time to slightly more complex mixed models for slightly more complex designs.